For 140 years, we've been enabling human progress, knowing that everything we do, everywhere in the world, is in service of people. Generations of our problem solvers all around the globe working brilliantly, collaboratively, and inexhaustibly to provide more reliable, more affordable, and ever cleaner energy. We've been in the business of progress since 1879. From the construction of our first refinery at Alameda Point, we've been delivering the energy that drives human progress and powers the world forward. Energy is vital to human progress, and our purpose is even clearer now than it was in 1879. 40% of the world's population has access to only basic forms of energy. Each of these global citizens deserves access to a better quality of life. Affordable, reliable, ever cleaner energy and the human progress it enables is essential to this basic right. We believe life depends on human energy.
Hi everybody, appreciate the opportunity to be with you today. My name is Nick Wan with Chevron. What I'm planning to share with you today is a couple of examples of how we are using discrete event simulation and specifically Simio in our capital projects organization to understand our projects as production systems, and through optimization of those production systems, ultimately improve the outcomes of those major capital projects. First, a quick introduction. Again, my name is Nick Wan. I'm a project execution advisor, which just means I get to go around the world to our different major capital projects and help teams implement best practices. One of the best practices that I get probably the most requests for is the implementation of operation science and leveraging those concepts to improve the outcomes of our projects. I did not go to school for this. My background is structural engineering, so I went to school to design structural systems, not production systems. Through my various career assignments within Chevron, I've had the opportunity to work both in structural engineering as well as a few other disciplines, mechanical, piping, even a little bit of process, both within our core operations as well as a part of our capital projects organization through project management and engineering management and these types of things, which is where I find myself today. So in terms of agenda, my intent is to share a project about a mine reclamation, and we'll talk a little bit about what that is. I'll also share a quick example of just kind of an engineering management example. It's probably a classic example that can apply in a million different ways and a million different knowledge work situations. And then we'll end with, we should have plenty of time for questions. And so yeah, let's jump. So I'll first start by talking about operation science, which was a concept introduced to us, well, I guess several years ago now, but was a fairly new concept to us. I'm sure many of you are familiar with operation science, which is the study of production systems, which as Project Production Institute describes it, focuses on the interaction between demand and production and the variability associated with either or both, right? So this is manufacturing type language. It doesn't initially resonate with a capital projects, construction project organization. We tend to think of our things slightly differently and bespoke, and but when we think more deeply about projects, they are production systems ultimately producing a product, which is the project. And to get there, there's an overall production system, but there's also multiple production systems that are feeding that overall production system. So we can talk through examples, but the idea that we can view our projects correctly as production systems, or maybe more accurately, compilations of multiple production systems, we can then, once we do that, we can then use operation science to optimize those production systems with the ultimate goal of optimizing the overall project and ultimately improving the outcomes of that project. Okay, so that's a bit of conceptual, but that's the logic we went through to understand that we can actually view our projects as production systems. Okay, so to this particular project that I was going to show you, this is a mine reclamation. So this was a mine that we acquired when we acquired a company. There's this mine that came with it. The mine did not really fit into our core operations and had kind of lived its useful life. And so, as we do with all of our assets, we have a plan to reclaim those sites, right? To basically put them back together again the way they were. So in this case, this is a mine that had been in operation for close to 100 years, and our objective was and is to reclaim this mine into a similar state as where it was originally found, right? So we spent 100 years kind of pulling the mountain apart to mine the rare earth material that we were looking for, and now we're going to spend the next actually several years probably putting the mountain back together again, you might say. All right. So we are looking, because this is a multi-year project, it's a little bit easier to see it as a production system. Lots of material is going to be moved. We have equipment that's going to be on site, and we want to utilize that equipment in an efficient manner. We want to make sure that we are operating that site safely. And there's a number of other things that we can utilize Simio to help us understand, right? But the logistical system, the equipment utilization system, how are we utilizing the resources we have to most efficiently execute this endeavor that we are embarking on. All right, so we actually did two different models on this particular site. I'll just mention briefly the second one that you see listed there is around stormwater runoff, and so we use the flow library within Simio to help us understand a little bit more about how stormwater was going to flow on site given kind of our ever-changing topography as we reconstruct this mountain, you might say. So had good success there. The one I wanted to focus on today is really this first one around truck haul route optimization, right? How many vehicles do we need? How many of these trucks do we need? How can we make sure that they are operating as safely as possible? Can we play with different sources of variability and make sure that we have a robust plan for the days and weeks and months ahead, and ultimately result in a confident, predictable schedule for this particular project? We did learn several things. In fact, some of the results that we found were not the results we were expecting, and so I'll get into that. So let's take a look at a video of this particular simulation. Okay, so here is our site. This is obviously a satellite view from Simio. Within Simio, you can see our paths laid out there. You can also see we've got a drone flyover of the site that it's constantly changing, so you kind of have to update the view within Simio with a drone flyover is what we're doing. You can see the trucks moving around. Generally what is happening is these trucks are going, picking up material from one location and taking them to another. So here's how our model works. At the beginning of the day, we can talk about how many trucks we have working in each location. So you may see the acronym PMCOW, PMCOW, that stands for Person Managing Control of Work. And so generally, each one of these trucks, or several of these trucks, are working for in a particular area where there's a person responsible for that area. So there's Pete's area. You're going to see Norm and Pete down here. So this particular truck that we're following is delivering material from Repeater, an area named Repeater, to Norm's place. So he'll go from one place to another. Now, what I wanted to focus on mostly in this conversation, this area known right here is Stairway to Heaven, and it's referred to that way because it's an extremely steep part of the site. And as you can tell, trucks are waiting here, right? They're queuing up here, and the reason they're doing that is because this, as I mentioned, is an extremely steep part of the site. And so trucks coming down in this direction are fully loaded, right? And you don't want to get in the way of a fully loaded dump truck. And then the trucks coming back up, such as this Pete truck right here, are empty, but they have to keep their speed up just to make it back up that hill, right? That's the general idea. And there was a near miss. Let me pause this right here. There was a near miss a while back at one point in the history of this project where a truck was supposed to yield and didn't yield, right? Something happened, and the person that didn't yield nobody got hurt, no, there was no incident, but it still got the attention of the site team, and they said, can we use this fancy model that you've developed to help us improve the safety, right? How can we minimize the probability of that event happening again? And so one of the guys said, well, why don't we just reverse the traffic, right? This is a one-way traffic right here, and so can we just reverse that traffic and not have to deal with that particular issue? So they said, well, let's model that, right? And so we modeled the reverse traffic. So now you can see these trucks are all going in the opposite direction. And so now they would be returning from up here. The question then becomes, are we actually solving that problem, or did we just move the problem? And so what we did is we came up with a parameter to kind of measure that, right? So we looked at all of these intersections here, and we said, look, have we had a net reduction or a net increase in the amount of traffic in those sites, a number of vehicle interactions? So we used a number of vehicles waiting as a proxy for vehicle interaction, because when a vehicle waits, they had to make a decision to wait, and they could have equally made the wrong decision to not wait when they should have waited. And so if we can minimize the number of vehicle interactions in this whole area, again, we can't focus on this one intersection, we have to focus on this whole area now. If we can minimize the number of vehicle interactions, then we can statistically reduce the probability that we have that particular incident again. Okay, so these are the results of the analysis, and what I want to draw your attention to initially here is these bottom charts, the left one being the original traffic route and the one on the right being the alternative traffic route. So anytime a vehicle is waiting in that intersection envelope, there's a vehicle interaction, right? The vehicle had to decide to wait, and he could have equally made the incorrect decision to not wait when he should have waited. Okay, in the model that doesn't really happen, but in real life, anytime there's a vehicle interaction, there's a potential for some sort of an event to happen. And so what we were looking at was, can we meaningfully reduce the number of vehicle interactions? And as a proxy, we use trucks waiting as a proxy for the number of vehicle interactions. And what we can see is effectively a 50% reduction in vehicle interactions. Now, what we were not focused on, but was kind of a nice surprise, was that we had a 6% increase in productivity, which makes perfect sense, because anytime the truck, we had a truck essentially at full time sitting there in that intersection. And so by reducing the amount of time that the trucks are waiting, we're increasing the time that they are doing something productive. And so we got a 6% increase in productivity. So this particular analysis was shared with the contractor. The contractual arrangement here is a bit unique, but the contractor did not have to take our advice. And so what we were doing was making recommendations to the contractor. However, they saw these results, and then the next day had their drivers practicing this new route. And by the third day, had fully reversed traffic on site. And so this is a good example of how we can use Simio to solve not only productivity problems, that wasn't actually the objective of this particular analysis, it's really more of a safety thing. And so we can use Simio to quantitatively optimize even safety performance on site. This is just one example. Now let's move to example 2. And this one probably also won't take all that long. Okay, so this picture may be maybe slightly more in line with what you anticipate Chevron being involved in. This is an offshore platform. And when you engineer an offshore platform, you create a bunch of drawings, right? So one of the types of drawings that you will create is what's known as a piping isometric drawing, which an example is shown on the right. And these are essentially used during fabrication to help fabricate all of the pipe that goes on one of these facilities. So you'll do the drawing, you'll fabricate this facility. In the case of an offshore platform, you'll fabricate it in a fabrication yard, and you'll take it out there in a pre-assembled unit and set it on the platform base or something of that nature, right? So generally, fabrication is going to drive the schedule for the engineering deliverables. Okay? In this particular case, we were fabricating we were fabricating in Korea, and the contract, essentially stated that we needed to produce, our engineering contractor needed to produce 100 piping isometric drawings per week, if I'm not mistaken. And so the project team, so the consequence of not doing so means that you have entire fabrication yards at a standstill waiting for engineering drawings. And so the consequences are actually quite high. And so the engineering team contacted me and said, look, we really need to make sure that we are able to hit 100 ISOs per week. And so I came in and we did a quick study with the engineering contractor and Chevron as the owner of this production system. So this particular project team uses this process in order to generate isometric drawings. So there's a drawing prep step, then those drawings are then checked. The certain amount of them are recycled, have to be reworked. Then they're going to go to scrubbing and back check. Again, a certain amount of them will be will fail checking and will need to be reworked. Then there's a quality control check, and again, some may be recycled. And finally, you get into issuing the documents and so on and so forth. Okay, so this is the basic steps. They also had identified number of resources they were planning to use for each step and duration, right? So they incorporated, because they knew I was going to ask for it, they added in average duration as well as some sort of a range. Okay, now we're going to focus on here is this checker and back check step, right? We're going to come back to this one, but on average, you'll see it takes an hour and a half per ISO. Okay, so let's focus on this check and back check step, and a kind of a traditional calculation that you would do to determine how many resources you're going to need would be something like this, right? So we've got, on average, it's going to take an hour and a half per ISO. It's not going to be perfect every time, so we're not going to assume it's an hour, but we don't want to be too conservative. So let's say an hour and a half per ISO. That's the average amount of time it'll take, right? That means in a 45-hour week, each individual person can do 30 ISOs per week, and therefore, if I need to achieve 100 ISOs per week, I need 3 1/3 checkers, right? And then what we'll actually just round up to 4, right? We won't be try to be too precise. So we've incorporated some variability, and we've been somewhat conservative. We've rounded up to a number of 4 checkers. So this should be a sufficient number of resources for this particular. And if we look back, we can see that that's essentially what they did. They intended to use 4 full-time checkers, and they even threw in a part-time checker as well. So, what might happen here is, an owner rep would say, well, look, I did the calculation. It says you should only need 4 full-time checkers. And they're trying to be a little bit conservative and say, I know, but I think we need a part-time checker as well, because maybe things just don't go quite as well as we have. And you can oftentimes find yourself in engineering management arguing over how many resources the contractor, as the owner, how many resources you're willing to pay for. And you can find yourself just kind of debating back and forth, number of resources without a whole lot more than the calculation that you saw on the previous slide as your backup. Now, so this is the result of the initial analysis that we did. So we actually found something fairly similar, right? So this is I ran the model as a con whip, right? So I maintained a constant work in process in the system, and I used experiments to run multiple different whip scenarios to identify what is our optimal whip level, right? So this is, essentially a graphical representation of Little's law, two different examples, right? So this is throughput versus whip, and this is cycle time versus whip. And as you would expect through Little's law, you can see throughput will increase up to a point, and then that's about all you're going to get. And what will end up happening is that inflection point is cycle time will start to increase. The two scenarios that you see here is one is with no variability, so everything goes absolutely perfectly, and we have no rework. And then the light gray line here on both of these charts represents, okay, we've got rework, but we have no variability in the process time. So in other words, if we said on average it takes an hour and a half, it takes an hour and a half every time, right? And so, again, this would seem to confirm that with the resources that we were planning to use, we should easily be able to achieve our target of 100 ISOs per week. Okay. Now, what's interesting is when we actually incorporate the variability that we discussed. All right, so when we actually incorporate all of the variability in terms of recycled isometrics have to be reworked, as well as the process time variability, we find something very different. In fact, our capacity of the system drops to only 81 ISOs per week. So what we thought was conservative, and in fact, with the extra part-time resources, the owner may have actually debated whether we needed that resources. Even with that part-time resource, we are not achieving the 100 ISOs per week that we are obligated to in the contract. And so the beauty of Simio is, okay, this is a problem. What do we do to... And so one of the next questions that you ask is, okay, well, what is causing this bottleneck? Where is the bottleneck, right? And the nice thing about Simio and discrete event simulation is that you can directly observe it, right? So we can run this model and directly see, well, here's where everything's backing up, right? It's between the check and the back check step. We can see that our resource utilization is high, 98, 99%. And it's like, okay, well, there's our first clue, right? There's where we should focus our first efforts around trying to debottleneck this system. One of the first ways that we did that was looking at the variability in the check step, right? So the check step was on average 75 minutes with a maximum of 4 hours. And so that's quite a bit of variability. And so we said, let's run some sensitivities on what if we could reduce that variability from 4 hours down to 3 hours, which is the orange line here, or down to 2 hours, which is this blue line here. And you can see if we could get it all the way down to 2 hours, that's quite a bit more in line with what we had anticipated the production of the system being. And so, okay, we haven't said how to do that, but we just said if we could do that, this is the impact that would have. All right, so another way that we could address that issue is, okay, we could add resources. Okay? So what if we add an additional checker, right? And that's another easy way to address this particular bottleneck. So we can just add more resources. It's not our favorite one because, again, as the owner, these are individuals that we're paying for. And so it does help us to achieve our objective, but is it the most cost-efficient way to do this? And so, but again, if we add an additional checker in this particular example, at 4 hours, we can still achieve 100 ISOs per week, although just barely. So the results of this analysis are summarized here in this table. So each one of these columns represents a different scenario that we ran. And so in this case, in this kind of left box over here, we've said we're going to keep the maximum check processing time at 4 hours. So we're not going to make any improvements over what our initial conversation said. And here's with 4 full-time checkers, we can achieve 82 ISOs per week. And here's how much we can achieve with 5, 6, or 7 full-time checkers. And so that's the way that would look like. And then now let's say maybe we are also able to make improvements into that variability around the check processing time down to 3 hours or even 2 hours, right? And so again, we're looking for 100 ISOs per week. So we're going to look through this throughput column of 100 ISOs per week, and we're going to find one of those that works for us, right? But we provided this as a table to the project, said, look, choose your own adventure here, right? This is the green highlighted boxes are what we recommend. Now, our recommendations are based not only on the throughput, but also on the resource utilization of the maximum, most highly utilized resource. So we feel like 85% is a good place to be, no more than 85% utilized in your bottleneck resource. And so that's where our recommendations come from, right? So we're looking for anything no more than 85% utilized and a throughput of 100 ISOs per week or more. Now, this concept of limiting the resource utilization to 85%, it's not an easy thing for an engineering manager or project manager to accept, especially when they've been taught to, maximize productivity and ensure you're getting the most production out of each individual resource. You never want to see anybody sitting around not doing anything. That's your job, is to drive production. It can be difficult to intentionally limit the utilization to 85%. But that's where our recommendations come from. In this particular case, the project team, if I remember right, did believe they could get their maximum check process time down to 3 hours. So they did feel like they were here. But they weren't quite ready to go all the way to 6 full-time checkers. So I think they settled on 5 full-time checkers. And they were successful, right? This project team was able to keep up with the work. They did get behind a little bit at times, I believe, but they were able to catch back up. And so that's a good thing, right? They were able to be successful, produce the engineering deliverables that fabrication required to keep this project moving forward on time and on budget, right? So that's it's a really good story, right? And the fact that the project team was receptive to the input. Okay. Now I do want to take some questions. I'm going to pause in just a minute here for questions, but I want to make a couple of points or observations here. If we think back to when I first described how you might calculate the number of resources, right? We said we actually think we need 3 1/3 resources to achieve 100 ISOs per week, but we'll round up to 4 and we'll say, look, that'd be conservative. We'll be conservative, quote unquote conservative, and we're going to give you 4 full-time resources. Well, the contractor proposed to the owner, well, we want 4 full-time resources plus a part-time resource. And so what could very easily have happened here is the owner and the contractor, and what probably would have happened is, if they hadn't looked at the project from this perspective, is the owner said, no, contractor, you're trying to pull one over on me. You don't need that extra full part-time resources. I've looked at this. You only, according to your own estimates, you only need 4 full-time resources. Okay. And that analysis did not take into account the variability that turns out to be quite important in this situation. Right? You think you're accounting for that variability by using the average and not some, best case scenario, but by not incorporating that variability, you're actually potentially underestimating what you need, and that's exactly the case here. But right, in that scenario, you would have had the contractor saying, "I need this," the owner saying, "No, you don't get that," right? And you would have had this debate. And the owner constantly trying to not spend any more money than they really need to, but at the same time they do want the project done, right? But they think they may think that the contractor is trying to pull one over on them, right? Where in this analysis we've elevated that conversation. This is not a subjective based on my past personal experience. This is, we've evaluated the production system, and this is what the math says we need, right? So we're not arguing and debating. We may seek to understand the production system and look for opportunities to improve it, but we don't have to have this kind of adversarial debate about how many resources we need. We can just let the model tell us as a result of the production system, and we focus on what actually matters, which is improving the production system, not debating the resources. And the interesting thing on this one was, in both cases, we would have both been wrong, right? The contractor, even with their additional part-time resources, from our perspective, would have still been underestimating what they actually need. And so in this case, it actually worked out to the contractor's advantage, because not only did they get their part-time resources, they actually got an additional full-time resource. And so anyway, I wanted to make that point. We're elevating the conversation to a much more mature place and becoming less adversarial in the process. Okay? The second point I wanted to make was, this analysis maybe took a week, right? They called me one week. By Wednesday, we were meeting in their office. By Monday of the following week, I had initial results. We iterated on it once or twice to what scenarios we wanted to run. And by Friday, the end of that week, I had produced this table here, right? So this is it's not a complex system, obviously, but it's also not a hard analysis to run, and it elevates the conversation, as I mentioned earlier, and it provides much more confidence in the predictability in the outcome of this production system and ultimately the project. All right, that's all the prepared material that I had for you today. I do want to say thank you again to Simio for the opportunity to present to you. I appreciate the interest in this topic. Be happy to take any questions that you may have.
Nick, how you doing? Good to see you.
Good. Hey, Adam, how are you?
I'm doing very well. Enjoyed that presentation. Thank you for that.
Yeah, of course.
For the folks in the audience, Nick and I collaborate often, so it's a nice change of pace here to celebrate this work publicly instead of our usual, which is working through it together.
Yep, that's right. Yeah.
All right, lots to dig into here. Let's start with questions from the audience. So, first one, when you reversed traffic flow to reduce interactions, vehicles ended up traveling longer routes. Did you account for additional cost, perhaps fuel wear time, and the grade of those new routes and evaluating whether the improvement was worth it?
Yeah, we did. So one of the other metrics that we tracked was total miles driven on this particular project. They were interested in that. Um, However, ultimately, this contractor was primarily driven by production. So we were certainly focused on improving the safety performance. And so when they looked at it, that's what they were primarily focused on. It turns out that they, in this particular scenario, the route is the same distance, and so there's really not a whole lot of additional fuel. And in terms of time, they actually end up saving time. Uh, I need to think about the grade perspective. Um, Ultimately, what they were focused on was the safety, but when they saw the production improvement, that's what they latched onto. And 6% production improvement may not sound like a whole lot, but keep in mind what this team is doing. They are reclaiming an old mine that took 100 years to mine. They're going to spend the next 20 years putting the mountain back together again. And so 6% may not sound like a lot, but that could result in months of schedule change.
Yeah, that's great. Our last presentation was about defining clear objectives when you set out to do a model. It sounds like that's exactly what you did. You focused on the KPI that was most important and delivered an answer there.
Yeah. This particular one was interesting. We even got down to modeling things like the porta johns and when do truckers stop for lunch and when do they go to the restroom, and so you can wind up in some interesting conversations about how long it takes to do a porta john stop. Um, so
Yeah, I mean, when you have a long run horizon, with a lot of repeated activities, little things like that can add up. So,
yeah.
understand that. That's funny.
So some of the we had several instances. So a lot of times what they concern themselves with is the spacing of the trucks. What ends up happening is these trucks get bunched up, and so we put in some controls around so we put in some uh, not one-way traffic but capacity limitations on the routes so that only one truck could go at a certain point, and then we would space them out using the model. um, and so they actually translated that to policies that they would apply on site. So a truck would get to a certain point and then they would stop and they would not proceed until they could see the next truck in front of them had already passed another point up ahead. So um, anyway, it was one of our first experiences modeling in this level of detail, and we had fun with it.
Terrific. That is great to hear. Let's see what we got next. All right.
Oh
I
boy.
think this maybe relates to kind of the stormwater
Yeah.
use case, right? So, um, anything you'd elaborate on as to modeling surface and subsurface water flow? How did you decide Simio was the right tool for that analysis?
Yeah, so we in this particular case we use the flow elements in Simio, and we were experimenting a little bit. They I wouldn't say that we settled on Simio being the best tool for that, but we were in this case we were attempting to prove that we could, right? And so they have these rainfall events in the in the winter that can cause some issues, and so they wanted to be able to run multiple different scenarios. And the way they were going to do that otherwise would have been to use some sort of hydrologic model that would have taken more effort. And so we can get some simple numbers. We understand the topography, so we can model in that topography. We know what pieces of the site drain to which culverts and that type of thing. And so we were able to do a simple analysis there. If we were doing something more detailed, I'm not convinced that Simio would have been the best choice there, but it, it's fairly simple. Those elements are allow you to do more than you would think.
Yeah, that's sounds like a little creativity was required there, but I'm glad
Yep.
glad it worked out.
Yeah.
All right.
Yeah, go ahead. All right. What outputs
What
ended up being?
outputs, yeah, ended up being most useful? Managers, contractors, operators. Did you extract data and build custom views or rely on standard Simio outputs? Looked like maybe some of both.
Some of both. Yeah, we did produce some dashboards. Uh, what teams that are not used to this, they get a lot of value out of the seeing the simulation, and and so they get really interesting when you can show them whether it's trucks moving or bottlenecks forming, and you can see the basic kind of initial model run in the facility view. The real power obviously is in the experiments and running multiple simulations and summarizing all of that information. So we end up either using a combination of dashboards within Simio or translating that data out into Excel or something like that. It's I've done several presentations for some of our leadership team, and they always love the simulation. They love to see things moving around. It makes for good presentations, um, but the power is in the data, which is which is a little bit deeper of a lift. So
Yeah, it's a good point, and not something to run from if the animation really generates excitement, because I think it is a real pain point to be at the boardroom level and feel like you don't have visibility, like you can't see the process.
yeah,
So there's value in that.
yeah, and in capital projects, right? In logistics or some other aspects of our company, it may not be that big of a deal. But in capital projects, we we struggle with the concept of we can view our projects as a production system. But once you do that, you can use tools like Simio and operation science to help solve problems that otherwise you would just be using rules of thumb. And so it provides a level of visibility that they would not otherwise get.
Terrific. Really good. All right, let's see what we have next. Yeah, I think it was a good discussion about variability, running some scenarios there. So, what might reduce variability look like as a business action, standardization, or training? And how does that discussion go in trying to get teams to commit to and understand that result?
Yeah. Um, right. Yeah. Because in the second example, we talked about reducing variability. We did not talk about how. We just said if you could do that, what kind of an impact would that have? So, in an engineering example, reducing variability um, could be things like training and standardization, uh, tooling to a certain extent as well. Uh, in a check step, generally things that are going to take that long are going to be things that are going to get recycled, and so you want to do things that will minimize any probability of things being recycled. So it could be introducing a an intermediate check upstream. It could be making people responsible for the quality of their product, like they do in Toyota. It could be any number of things, but standardization is certainly one of those. Training, certainly one of those. in an engineering environment where we're working in an engineering contractor's office, we as an owner will have less control, but sometimes in knowledge work, it's just about communication, letting people know what is coming, in this case, isometric drawings, which isometric drawings are up next, and starting to make a plan for, or do we have all of the right pieces in place to be able to complete that particular isometric drawing when we start it. And so a little bit of pre-work there may help with that. And we could do that off
Yeah.
of the critical path, right, or outside of the bottleneck.
Yeah, I mean, this topic excites me because the industry talks about digital twin now, but this is really core simulation. Do some curve fitting, include a distribution, run replications, and even exposing the impact of that variability presents risk to the business. So if you're not meeting targets, then you have some sense of sensitivity analysis and like that bullwhip effect. So I was really
Yeah.
glad you presented about that. Let's see what we have next. Yeah, I like the questions about validation. Can you share about how you validated against reality? What did you compare against? And how did you know, how did you build that trust that the model was valid enough to drive scenarios, drive decisions?
Yeah. So I'll speak maybe about that first model. So in that model, we were obviously modeling those trucks, and that's something that we can directly measure. So in that scenario, was working with a construction supervisor. So this is not a engineer, but they certainly know their work. And so we took initial estimates at how long we thought each one of those trucks would drive, what speed limits they had on site, how all of that would work. And then he would go out there and he'd spend an hour or two every once a week, and he would just use the stopwatch and actually measure the trucks. And so he got really energized. The other piece of this is while we were building the model, I was doing some of the work, but he was doing it as well. And so he was actually modeling. And so with the kind of out of the box features in Simio, we got a construction rep doing his own Simio models, which I think is a pretty interesting thing, right? The barrier to entry is pretty low there.
It's amazing to hear. And yeah, sometimes the old fashioned, just go and look at it and make some measurements yourself is a good validation strategy.
Yeah. Yes, and that, I mean, it's important because if you don't, then nobody's going to believe the results. And so so he had not so much the model, but he had earned the trust of the contractor because they knew he was out there measuring things and he wasn't just putting some perspective on it. He was attempting to remove as much bias as he possibly could.
Yeah, I mean, that is a core aspect. And when I think of it, it's like convince myself first and then,
Yeah,
present back to the business. So,
absolutely.
all right, let's see what we have next. Yeah, you talked about that proxy concept, which I thought was really interesting. Could you elaborate a little bit on how you landed on that choice, the truck's weighting, and any other noteworthy cases where you had to be a little creative about how to model it?
Yeah, so some of that honestly was perhaps my skill set at the time, right? What I knew how to do in Simio, and and that was an easy one. I could use the out of the box features, the kind of um, the standard nomenclature around measures and things, and I could easily tell when vehicles were waiting. That particular one, like I mentioned before, uh, anytime a vehicle was waiting, they had to make a choice to wait, and they could have equally made the incorrect decision to go when they should have waited. And so it seemed like a reasonable proxy for what we were trying to achieve there.
Yeah, and one of my colleagues has said that you don't have to know how to do everything in Simio, but knowing how to figure stuff out is a really good skill.
Yeah,
And it sounds like you applied that and used the resources and figured out an approach that worked.
yeah. The important thing there was we had to make sure that we could easily address the issue right there. But Dad, we really reduced the traffic on site, and so that's where we looked a little bit more broadly into this area, this envelope around the stairway area, and we're able to validate that we had indeed reduced traffic overall, not just in the one particular intersection.
Good stuff. All right, let's see what we have next. Yeah, I think you alluded to one, but can you talk about cases where the results perhaps weren't what was expected, and how that discussion typically goes with the business?
Yeah, we have had that for sure. Um, I'm thinking to these models, but other models as well. Um, when we were first introduced to the concept of viewing our projects as production systems and then attempting to use operation science to improve the performance of those production systems, we started with some analytical tools to try to understand that. The problem that we found with analytical tools was it appeared to be a black box, and nobody really understood what was going on in the black box. We couldn't see it. We couldn't uh, feel it. We couldn't, we couldn't observe the behavior. And so when we would get results that were counterintuitive or weren't what we expected, the natural inclination is, well, I don't understand. It's a bit of a black box. I'm not going to trust it. So we've had this issue. So I mentioned the model around the engineering drawings. A couple of years ago, we did the same analysis using an analytical tool, and the project team, we got similar results, slightly different, but we got results that weren't quite what they were expecting. And because they didn't understand how the model was developed and how the results were being generated, they said, we've been doing this a long time, so thanks, but no thanks. We're going to do it our own way. What they ended up finding was about 6 weeks into that project, they were falling behind and they ended up having to mobilize additional resources to catch up. And by that point, your options around reducing variability tend to be less, and so all you can do is throw resources at it. So we've had that exact problem before. What I think made the difference here was perhaps a different team that was more open to the feedback, but the fact that they can see the buildup forming, they can see where that bottleneck is, and that made them much more receptive to the results.
Great. Yeah, we like to talk about Simio as a glass box versus a black box because you can really use the
Mm,
tools of the software to see why you're getting a result.
yeah, I like that.
What do we have next? Yeah, do you see these models living on after the initial project
Mm.
wraps? Is there a model owner, refresh cadence? Have you played that role? What does that look like?
Yeah, so that's a good question because in our case we are primarily looking at least in my case within Chevron, we're primarily looking at projects which are temporary production systems, which end up going away, and so uh, in many respects the model will retire with it. But we have used the same models over as a template for the next project. And then the other example that I'll say is in at least one of our businesses, we modeled a logistics similar to the truck model, and they, as part of a project to ensure that we were going to be able to deliver the materials for the project when they were going to be needed. The business then observed that model and then took it over and started to has expanded the model to incorporate the entire logistics system for that business. Uh, Maybe that's a bit strong. It may not be the entire system, but they've taken the model and expanded on it and made it evergreen. And so in that case, we have done some of those. We are working on other models, not in our major capital projects organization, which will obviously be live, right? And we'll do much more fancy, sophisticated things that probably most of your customers already do. Linking it to ERP systems and things like that. We're kind of anxiously anticipating that.
Yeah, I mean, sometimes in a design context or with capital project, you run the model, get your answer, and you're good to go. In other cases, keeping it plugged in makes sense. So,
Yeah,
yeah,
the other thing that the questioner mentioned there is there an owner, and that would be an important thing. In the case of the model that the business took over, that's exactly what they did. Is they identified somebody uh, that had the skills to manage and expand that model, and that's what they ended up doing.
Very nice. All right, let's see what's next. When debugging an unexpected behavior, where do you typically look first?
Oh boy, that's a good question. Um, I guess I would start by validation. So in the case of the truck model, I would first go look at validating that the unexpected behavior is not just my bias or my perception, but it's observable. And so in cases where it is observable, we would go measure and we would start there, and then I would probably take a fairly linear track and just start tracing it backwards. Um, I don't know, Adam. This is a good one. I mean, there may be more sophisticated approaches at doing this, but I'd probably just take a dumb approach and start looking for where I see the behavior that looks wrong, and I'd start there.
I like the simple approach here, just a good old fashioned root cause. One of my policies is really find what the problem is before I start trying to fix stuff.
Yeah.
Because there's a temptation to be like, oh, I'll try this, I'll try that. But using the trace, using the watch, really digging in until I figure out, did I model something wrong? Or do I have problem understanding the process? But no, I think you stated it well.
Yeah, the tools that you've got built into Simio around trace, I didn't use until you showed it to me about maybe a year ago now. But for that's would suggest I did it without trace for a year and a half, and so it was kind of eye opening when you showed me that. So there's a lot of built-in tools that can help there.
Yes, that's a good message for any new modelers. Is use the debugging tools. If you don't know about them, reach out and we'll tell you about them.
Yeah.
Let's see what we have next. So I think this refers to kind of the isometric drawing work. Someone was really eager about it. Is this written up anywhere or published?
Um, it's not the concept of viewing projects as production systems, and specifically engineering application, that is not by us. This particular example is not, but that is that concept is certainly gaining more traction in our industry, and is published through organizations like the Project Production Institute. They've got some examples of that. It wouldn't necessarily be Simio, but that it would be that basic concept. Um, but happy to talk more if somebody wants to reach out. We can exchange notes. Um, yeah, happy to do it.
Appreciate that. I think just two more questions, then we'll wrap up. What surprised you about the flow library, other than everything? And what advice for someone whose first instinct is to force a flow problem into DES or vice versa?
Yeah. So actually, I was talking with the team about this yesterday. That um, is looking at a pipeline application. We're trying to determine if Simio is the right tool for them. The first thing that I noticed about the flow library was that it was pretty simple to use. It's got the basic tools that I need. If you are looking at merging flows, um, it's a pretty clever way of doing it, and it's simple and it's not overly complex. Now, in our business, we deal a lot with hydraulics, and the flow library is not a hydraulic model. And so this is what I was talking with the team about yesterday: is if it's if the application is more hydraulic in nature, Simio, I don't know that that would be the place I would start there. But if it's more mass balance, volume balance type of thing, it actually is pretty good. Where I have struggled is um, in splitting flows to, even though it's not a hydraulic model, we may want to split flows in multiple directions, and you have to tell it what to do in those situations. So it can be a little bit challenging. So I think my advice would be, um, evaluate the problem and make sure Simio is the right tool. And I don't think Simio would mind me saying that, because we don't want to oversell the tool and you end up giving it a bad name, right? So, um, but yeah, I think that's that's probably what I'd say there.
Yeah, I think that's a great answer. And the only thing I would add is it's worth asking the question of flow or no flow. Can we, discretize packets of something that we
Yeah.
want to send along? Maybe if there's like a daily change, sometimes that's an okay approach, but just depends.
Yeah, you've said that before, and I think that's wise. Make sure you aren't forcing the wrong problem and your problem into the wrong tool. We have done several examples of where we've taken flow and then they end up being discretized, right? So a a pipeline brings oil to a marine terminal, which is then loaded onto a vessel, and so that vessel departure is obviously a discrete event, and so then as the vessel leaves, the tank starts filling up again, right? And so those are actually quite useful applications for Simio.
Very good. I think we're gonna do one more question. And Nick, just fact
Mhm.
check this question. I'm trying to remember. Was there an 85% utilization ceiling? What was that conversation like with management?
Yeah. So this is a good question. And the answer is we don't always get this right. This is what we advise. Um, in the case of the model you saw today, we ended up meeting in the middle. We proposed something in 80 to 85% utilization, but it just goes against managers everything they've been taught to intentionally have utilization below 100%. And what we find in operation science, right? So Kingman's equation talks about the higher as utilization approaches 100%, cycle time goes to infinity. And so we've had some luck, with explaining that concept to them. Oftentimes, it's a bit of a negotiation. So we say, look, 80 to 85% is what we advise, and then we let them make their own decision. Um, uh, when I went to the Toyota factory a year or two ago, I think I heard them say their their standard utilization somewhere in the 60 to 70% range. If Toyota's at 67%, what makes me think I can be at 100%? So that's it's my philosophy. Sometimes it is accepted, sometimes it's not.
I think that's a great place to leave it. Nick, awesome discussion. Really appreciate the talk, and I'll chat with you soon.
Yeah. Thanks for all the questions.